Welcome back to part 3 of our series where we are talking about portfolio optimization using the Python programming language. Now, in our previous video, we focused more on collecting the data from the NASDAQ website and then loading that data into a pandas data frame, at which point we could then transform it to get it in the proper structure. So that way we can move on to the portion that we're currently on, which is calculating the different metrics necessary. So before we actually jump into doing the actual calculation of a single, I would say iteration, if we want to think of it from the Monte Carlo perspective, it does help to understand kind of what is going on behind the scenes with the math and really what's the overall goal here. So I do have this part of the notebook, and I would encourage you, if you have some time, to look over it and just read through it. I think most of this stuff is pretty interesting, but I think it helps frame the problem as to why do we approach looking at portfolios in this fashion. So to kind of start things, a lot of times we've seen, obviously, in the financial world that a lot of people are competing for business, right? And there's many different types of fund managers out there. There's many different types of financial advisors out there. And naturally, a lot of the time, something we want to do is we want to benchmark different managers, to say, well, who should I go with? Because if I have some type of benchmark, ideally that can help me bucket managers into different performance levels. So I could have a really good performing manager and I could have a really bad performing manager. So I need some type of benchmark to say, hey, how do I help distinguish one manager from another? I might like them really both, but if it comes down to performance, I'm more than likely going to go with the one who has a better track record of performance. And so one benchmark that we could look at is just saying, well, how much money did they make you, right? So maybe I'm comparing John with Sarah, and I'm going to be saying, well, Sarah got me a 15% return and John only got me a 10% return. So I'd say, I'm going to go with Sarah, right? Sarah got me a higher return, love more money. So naturally I should go with her, right? Well, then maybe John comes back and says, yeah, but Sarah took on a lot of risk. And when you look at it, it's not necessarily like she did that much better. So he might be saying, yeah, my return's lower, but when you look at how much risk I took, I actually did really well compared to Sarah. Because Sarah, yeah, she got you a better return, but man, she took on a lot more risk than I think you should have to. And so one way that we can kind of benchmark different managers is we can use something called the Sharpe Ratio, like we've talked about earlier on in this series. And with the Sharpe Ratio, what we are trying to do is we're trying to use it in order to measure something called the risk-adjusted return. And so the idea behind the risk-adjusted return is we're not going to just say, well, here's a return, that's all you need to think about. Instead, what we're going to say is, well, here's a return, but when you take the risk of the overall portfolio into consideration, this is really how much of your return that you got. And so when we say a risk-adjusted return, there's also another important metric that we have to put in there, which is something called the risk-free rate. So the risk-free rate is basically the rate that you could get by taking on no risk. Now, it's a lot of people kind of say, like, it's a really such thing as no, like a kind of a free lunch, right? It's a really such a thing as a risk-free rate. And, people will debate it, but, generally speaking, when we talk about the risk-free rate, we would say, well, what is the return for a United States Treasury, right? Because the idea behind a United States Treasury is that the US is never going to default on its debt. At least that's the idea. And so if you invest into a United States Treasury, you're pretty much always going to get your money back. So you would basically say this is the risk-free rate. This is free money. You don't have to take on any risk. You just get it every single time, regardless of whether you put the money in or not. So it's a risk-free rate. And so when we calculate the Sharpe ratio, the first thing that we do is, you'll notice at the top, is we take the difference between the return of the portfolio minus the return of a risk-free rate. So we take the return, basically our risk-free rate. And the idea behind it is really what you are looking at is how much of that return above the risk-free rate did you get. So ideally, you want your return of the portfolio to be a lot higher than the risk-free rate, because then what you're saying is, wow, you're getting a bunch of return. However, in order to kind of normalize that and take risk into consideration, we divide that difference by something called the standard deviation of portfolio's excess return. So basically here we're saying how much volatility maybe is in that portfolio, how many swings up and down do you get? And so the idea behind here is, do the returns vary an awful lot? Do one year you get 1%, then the next year you get 30%, then the next year you get minus 20%? If there's a lot of volatility, there's a lot of uncertainty. You don't know one year if it's going to be up or down. And so what that's reflecting is there's volatility and that the risk is going higher because you don't know what's happening. One day it's this, one day it's that. Ideally, you would like less volatility because it's more predictable, right? So if I know that every year I'm going up 1%, yeah, it might not be going up a ton, but it's very consistent. So there's not a lot of volatility. And so the idea behind it is you want a very steady, large return, ideally, right? So ideally, you would like a large return that doesn't deviate very frequently. It's pretty much consistently staying within that range, ideally. Now, we all talk about how do you find an investment like that? There's many different ways, and there's a lot of skeptics out there, myself included. Usually if it sounds too good to be true, it's too good to be true. And so we use the Sharpe ratio as a benchmark to compare maybe one portfolio to another portfolio. And it helps us understand how we can distinguish one from the other. Now, something else I always like to say is, well, what is considered a good Sharpe ratio? Well, ideally, anything below 1 is not super great. So 1 is considered suboptimal. 1 is kind of your benchmark of like, okay, well, here's your C grade. It's not great, but it's passing. An excellent Sharpe ratio tends to be around 3. So ideally, we'd like something higher. So a higher Sharpe ratio is a better performing portfolio. So we want a higher number. Now, to kind of just demonstrate a little bit of the math, imagine I had an expected return of 10% and imagine we had a risk-free rate of 5%. Well, we don't have that right now. It'd be very nice, but imagine we had a 5% risk-free rate. And then we had like our adjusted excess return, or the risk return aspect is like 2%, right? Just leave it at that. So the return above the risk-free rate is 5%. So your Sharpe ratio is 2.5. So that's actually really good. That's actually a decent Sharpe ratio. It's definitely nothing to complain about. But you can see the math behind it isn't super complicated. But naturally, some people might ask, like, well, what if the expected return was 4%? Well, my first question to you would be, why are you investing in this? Because basically what you're saying is you're willing to take a less return than the risk-free rate, which doesn't make logical sense for most people. I mean, I guess an economist could come out there and argue why that might be the case. But, rationally speaking, if you could get a 5% risk-free rate of return, you would go with that. You wouldn't take a 4%. So if you go negative, you've really got an issue. If you're at 5%, well, then you have a Sharpe ratio of 0, because basically, again, what you would be saying is, well, just go and take your risk-free rate. Why would you take any risk if you can get the same return for no risk? If we go to 6%, you can see it's not great, but you can see as you get a little bit higher, you get a little bit better. And so now you're saying, okay, well, now you're 7%. So you're doing a little bit better. So, it's just all this that you have to take into consideration when you're thinking about how do you use this Sharpe ratio as your benchmark. Now, in order to calculate the Sharpe ratio, we've already talked about that. If you want to calculate expected returns, it's actually not too bad. What you would do is you would just take the weight of each asset in your portfolio. So if, say, you have 5 stocks in your portfolio and say each stock represents 20% of the total, then each stock has 20% weight. And then you would say, okay, well, what was the return of each stock times that individual return by that individual weight? And then you would add all of those products together to get your expected returns of the portfolio. And so this is not too hard to calculate. Most people, when you look at that, you can kind of logically think through like, oh, okay, like I see what's going on here. You're just taking each individual asset. You're saying, how much does it take up of my portfolio? Once I know that, I can just take that particular asset's return And that's how much it contributed to the total return of the portfolio. And the same logic can be used with standard deviation. It's the idea that each individual asset has its own kind of variance and spread of returns. And you're going to say, well, I know how each individual asset changes over time. So I can say, well, just take that variance and say, okay, well, that makes a lot of sense because I can just take the weight of it and do the same logic. But then at the same time, you also want to take the correlation coefficients between each of the assets as well. So that's another idea when you go into portfolio theory, is that some things can be very correlated together. So when one moves up and the other moves up, they both move up together. And so you want to take that into consideration when you think about the overall movement of the portfolios. You really have to ask that question as well, how do each individual asset move with regard to the entire portfolio? And so it just adds a little bit more complexity to the calculation. But again, when you kind of think through it, it makes a little bit of sense. It's not super difficult once you sit down and say, okay, wait a minute, I understand what we did here. I'm just going to apply that same logic here, and I'm just going to add this kind of extra component to it to take this other concept into consideration. So this is basically duplicating this, and then we're adding a little bit of an extra fluff in there to capture another idea. And then ideally, we want it not to be the variance. We want it to be a square root, because then I can put it in terms of units. So I can say, well, for each dollar you get, this is how much risk you have to get potentially. Or for each percent of return, this is how much risk. With variance, you're just saying, well, this is how spread out it is. With a standard deviation, you're saying, well, here's in a per unit term per se of what you can get. That's at least the idea behind it, is I can put it into something that's bite size and I can, increment. Okay, so now that we have that under our belt, we're going to move on to actually calculating these metrics. Now, what I'm about to show you is basically what we would be doing for the Monte Carlo simulation, but I'm basically saying, let's just do one iteration to see what is going to be happening behind the scenes when we run this Monte Carlo simulations thousands and thousands of times. So you can think of this next step of saying, let's imagine we just do one iteration of that Monte Carlo simulation. What does that look like? What does that look like? So pretty interesting stuff. So the first thing that we need to do is we need to calculate the log of returns. Now, a lot of people say, Alex, why are you doing log returns? Well, it boils down to when we're talking about returns, we want to take this idea that these are returns over time. And so the idea behind this is when we take a percent change, what we're going to be doing is we're going to say, well, what is these changes over time? And so a log return is just a better kind of capture of that idea of returns over time. When you talk about something like just, hey, what was the actual average return? Then this is something you would say is more related to specific assets. So just over certain returns, what's the average? So the log return helps capture better the idea of returns over time. So calculate the log returns, or the log expected returns ideally. And then from here, well, I guess it's not really expected returns, really it's the log return, but we're going to do log return equals numpy log. So there's a log function, and then it's 1 plus, we're going to take our price data frame and we're going to use the percent change method. What that's going to do is it's going to do the percent change one row to the next. So one row to the next, you're going to get your percent change, and it's basically going to make it where each one is over time. So that's pretty straightforward, and we don't have to do any crazy modifications, because again, part of organizing it here is when we do calculate it, each column is their own source of data. So it's not like we're having one row for Square, one row for Apple, and so on and so on. That would make it a little bit more challenging, but because we've organized the data in such a way, it's now very easy to calculate this metric. Now, something we need to do is whenever you do something like a Monte Carlo simulation, a lot of people say, well, where should I start? So the first thing we need to determine is, well, what weights should we give each of our assets in our portfolio? And a lot of people say, well, where should I start? Here's the answer. You just randomly guess. Sometimes the best place to start is you just randomly guess. And then what you're going to do is you're going to run these iterations so many times with so many different random values that over time, if you do enough iterations, you should be able to capture the variation aspect of it. So what we're going to do is we're going to just generate some random weights. And it's going to be very important that we notice something about these random weights to begin with. So I'm going to do random weights equals numpy array. And then it's going to be numpy random dot, is that the one? I hope that's the one. Random dot random. And then it's going to be, we need 4 random weights. We need 1 weight for each symbol in our portfolio, or 1 for each asset in our particular portfolio. So again, I can take this information that I calculated up above. So that's pretty good so far. And then what we're going to do from here is I'm going to display this for you. So I'm going to display the random weights. Now I just opened up my notebook again, so I do have to run this one more time just to make sure that we can get everything nice and wonderful stuff. That's right, I have to install it here. Sorry. I deleted my old one, so I have to reinstall it. It's not going to take that long because I already have most of the stuff again. Perfect. Wonderful. Okay, and then I need to restart the kernel because, yeah, that's fine. That's always the problem, is when you do this sometimes what happens is it doesn't like it. And then, of course, it looks like it's still not going to like it, so that's always a good start. Woo, goodness. Trust it. Okay, so that seems like it worked this time. Okay, sometimes you have to do that with Jupyter Notebooks. You just have to run it and to close it down because otherwise it doesn't work for some weird reason. That works, that works. So let's take a look at our random weights. And you're looking at this and you're going, oh, this is great. I got random weights. But this doesn't make sense because 61% of my portfolio goes to one, then 20 goes to another, and then 26. So wait a minute, this doesn't make sense, because what you're saying is I can have a portfolio that has more than 100% allocated to it. That doesn't make sense. We can't use these numbers. So we actually have to do another transformation, which is we need to now make it where these random weights are really our rebalance weights, because right now it's equaling to more than 1. I want all my weights to sum up to 1. I want them to sum up to 1. So generate the rebalance weights. And then these ones, they must equal 1. So I'm going to say rebalance weights equals my random weights. And then I'm going to do a little bit of math trickery. It's nothing super fancy. I'm going to sum the random weights. So I'm going to say take the total and say how much does each random weight represent of the total of all the weights. And then you'll see some magic here. And you're going to say, wait a minute, Alex, what are you doing? Look at that. So now this will now sum to 1. It might be slightly off sometimes when you compute this stuff. It can be off by very, very, very small amounts, but ideally it's not going to be anything super noticeable. So don't get too, comfortable with that. Keep in mind it could be a little bit off, but we want it to 1. So we want it to equal 1. And then what we're going to do from here is we're going to calculate the expected return. So now we're taking our log returns and we're going to calculate the expected returns. Well, how do we do that? How do we take and calculate our expected returns? Well, that's not too complicated. We're going to take our numpy, we're going to call our sum function. And then inside of that, we're going to sum the log return, the average of the log returns. And then I'm going to times that by the rebalance weight. So I'm going to say, if I take my log returns, because I did up here, I took the log returns for each symbol, and I'm going to say, okay, the average log return times the weight, because remember, I have to take my weight. I'm not going to say that my entire portfolio represents the square return. It represents the square return, the Microsoft return, and the Amazon and the Apple, and so on and so on. So it represents more than just one return. And I'm going to take each individual return, times it by their weights. And then I got to do one little final trickery, which is times it by 252 to annualize it. So calculate the expected returns annualized. That's where the 252 comes from. Why do you do that? Well, it's just kind of common convention. You annualize it because you're really looking at things in terms of what is it? In terms of the calendar year. Now, remember, these are average daily returns times 252 days to get your annualized returns. Oh, don't you love all this math? Okay, so we calculated the expected returns. Now we're going to calculate the expected volatility. So is it moving up a lot? Is it going down a lot? I don't know. It's calculate the expected volatility, and then again, annualized. So expected volatility, it's a little bit more complicated because obviously we can tell here we have to calculate our correlation matrix and all this kind of fun stuff. So bear with me. So we're going to first start with our square root. Everything is under a square root. And then we're going to say, okay, well, we need to take the dot product. So we're going to say MP dot. And then again, so this times this. We're going to take our rebalance weights and we're going to transpose them. And then we're going to take the numpy dot function as well. We're going to take that log return. We're going to calculate the covariance of it and then times it by 252. And then we're going to do our rebalance weights. Okay, so complicated formula, I understand. But just keep in mind, all it's really doing is you're taking your expected volatility and you're just basically taking the weights, you're transposing it to get ready for a little dot product in a sense, and you are calculating you're basically timesing it by the weights times the covariance aspect times this. So this is just doing, again, some matrix multiplication, everything like that, in order to be a little bit more fancy. It's a lot of math trickery behind the scenes because really we're just doing what we're doing here, but we might do different methods that arrive at the same result. So don't get super intimidated by this. Just keep in mind, we're just calculating the standard deviation of the portfolio, the expected volatility in a sense. So that's all we are saying here. And then from here, guess what we can calculate? We can calculate the Sharpe ratio. Now, in this situation, I'm being very specific. I actually don't have a risk-free rate. So in a certain regard, it's a little bit misleading, but I guess I could add it in if I wanted to. But for just the time being, we're going to do expected returns divided by the expected volatility as well. So you could also add in the risk-free rate if you wanted to. So you could do something like, I don't know, maybe 1% or something like that. And then what do we get for our Sharpe ratio? Well, we'll take a look at that in a second. The next thing I'm going to do is I'm going to put all of this information into data frames so we can more easily see it. And so that's just a lot of typing, doing a lot of kind of stuff we've been familiar with. So I'm going to just actually copy that code because it's really just creating two data frames and then printing out a bunch of different lines. I don't think it's super informative what we're going to be seeing. And I just realized that's 10%. Let's do something a little bit more reasonable because we definitely are not getting a 10% free return. It'd be nice. It would be very, very nice. But you can see here, I'm creating a data frame and I'm just going to have random weights, rebalance weights. And then here you can see I'm just printing out so it's a little bit more readable. And then with the data frame, I'm putting the expected portfolio returns, expected portfolio volatility, and then the portfolio Sharpe ratio as well. So if I print this out, you can see here were our random weights. We made them where they all sum to 1. So here's our rebalance weights. And then our expected portfolio return is very good. It's apparently 114%. Wow, that's exciting. That's a lot. expected volatility, and then our Sharpe ratio is 3.19. So that's actually really good. I guess for the amount of volatility that we're taking on, that's interesting. But I mean, if you think about it, I guess, I mean, these are all pretty hot stocks. I mean, Amazon is definitely a hot stock. I mean, 3,000 from 2370 to 115. I mean, this is almost doubled. This, this hasn't doubled, but trust me, given from the beginning here. And then this, I mean, Microsoft always moves pretty steadily. Even when there's volatility, it doesn't move crazy amounts per se. I mean, this is kind of a crazy jump, but that was right during the height of the pandemic. So I guess that's not too crazy. Square, they're almost doubled in price. I mean, they have doubled in price, almost tripled in price. What am I saying? So, I mean, a lot of these stocks have done very well. I'm sure there's some volatility, but it doesn't seem like it's that bad, but it seems to be doing pretty well. I guess if you have money, maybe I should be investing in this. I don't know. But that's basically what's going to be happening behind the scenes when we're doing the Monte Carlo simulation. Is we would be doing something like this. We're going to be calculating the expected return. Once we have the expected return, we're going to subtract the risk-free rate to get the actual component of it. And then from here, we're going to also calculate the expected volatility. And then we're going to do this a bunch of times with a bunch of random weights. And then whatever comes out as the best result, guess what? That's how you should balance your portfolio, ideally. So at this point, if you have any questions about calculating the log return, calculating the random or rebalance weights, the expected return or the expected volatility, feel free to put that down in the comments below. If you have just any general questions about the Sharpe ratio or any of these kind of calculations, feel free to put those down in the comments below. In our next video, we are going to continue on and we're going to run our Monte Carlo simulation. So we're going to basically be doing what we did here, just a few more extra steps. It's more about just building these pretty big arrays to calculate, to store all these different values as we calculate them. And then from there, I think we will be doing the optimization aspect of it. So that's what we have coming up. If you are new to the channel, feel free to subscribe as well if you're liking this video. So if you have suggestions for new videos, I'm always happy to hear that as well. There have been a few who have suggested videos and I very much have done topics on it. So feel free to submit an idea if you think other people would enjoy it. So thank you again for watching, everybody. We'll see you in video number 4.